In this lecture, I will explain the system of harmonic oscillator as an example of a system in canonical ensemble. We will treat classically and quantum mechanically. So first we will discuss the classical treatment of harmonic oscillators. Suppose we have n independent harmonic oscillators. The Hamiltonian of ith oscillator can be written as h of qi pi is equal to half m omega square qi square plus pi square divided by 2m, where qi is the coordinate of the ith oscillator and pi is the momentum of the ith oscillator. This I can take values 1, 2, 3, etc. up to n. There are n independent harmonic oscillators. Now we will calculate the single oscillator partition function, and it is q1 of beta is equal to this. We will use the phase space concept, integral minus infinity to infinity, integral minus infinity to infinity, because the phase space of a single harmonic oscillator is two-dimensional. We have only two variables q and p. So integration of q from minus infinity to plus infinity and p from minus infinity to plus infinity. E raised to minus beta h. Instead of h, I have half m omega square q square plus p square by 2m into volume element of phase space. It is dq dp divided by the volume of a microstate in the phase space, and that is given by h. That is given by h. Now q1 of beta is 1 by h will come outside, integral minus infinity to plus infinity, e raised to minus square root of beta by 2 m omega square q the whole square dq, integral minus infinity to infinity e raised to minus square root beta by 2m p the whole square dp. Okay, now substitute for square root beta by 2 m omega square q as x. Then dq is square root 2 by beta m omega square dx. And similarly, substitute root beta by 2m p as y. Then dp is square root 2m by beta dy. Substituting this into this integral, q1 of beta becomes 1 by h integral minus infinity to infinity e raised to minus x square root 2 divided by beta m omega square dx, this quantity. Then integral minus infinity to infinity e raised to minus y square root 2m by beta dy. These constants I can take outside. This root 2 and root 2 becomes 2. Denominator there is a root beta, here is also a root beta, that becomes beta, and square root of omega square becomes omega, and there is already an h here. This root term in the denominator and root term in the numerator will cancel. Remaining is integral minus infinity to infinity e raised to minus x square dx, integral minus infinity to infinity e raised to minus y square dy. We have the standard expression for this integral, and it is root pi. Similarly, this also is root pi. So root pi into root pi becomes pi, and you can take this 2 pi into the denominator of h. So h by 2 pi becomes h cut. So this is simply beta is 1 by beta is kt. So that is kt by h cut omega. This is single oscillator partition function is given by q1 of beta is 1 by beta h cut omega or kt by h cut omega. This is the partition function of a single oscillator. Now, for the n oscillator system, we can write the partition function as qn of beta is equal to q1 of beta raised to n. In our actual expression, if the system is indistinguishable, there will be a 1 by n factorial that we discussed in the earlier classes, and here we are treating the oscillators are distinguishable, so no need to write the 1 by n factorial. Substituting for q1 of beta, as kt by h ket omega. You will get qn of beta as kt by h ket omega raised to n. Here kt is nothing but 1 by beta. Now we can calculate the different thermodynamic parameters of the system. First we will calculate Helmholtz free energy. A is equal to minus kt log qn. Substitute for this qn. Log a raised to b is b log a. So this n will come to this side. So this is a equal to minus nkt log kt by h ket omega. This minus you can take it into the log and that becomes inverse, okay, because minus log a you can write it as log a raised to minus 1, and that is why this kt by h ket omega becomes h ket omega by kt, h ket omega by kt. Call this as equation number 4. This is Helmholtz free energy. Once we have Helmholtz free energy, you can take the partial derivatives with respect to n, with respect to v, with respect to t in order to obtain chemical potential mu, pressure p and entropy s. So chemical potential mu is dou A by dou n at a constant volume and temperature. So take the derivative with respect to n, you will get kt log h ket omega by kt. That is the equation for chemical potential. Pressure is dou A by dou V at a constant n and t. There is no V dependence, so the pressure becomes 0. Entropy is minus dou A by dou t at a constant n and v. There are two terms which contains t. This nkt has t dependence and this h ket omega by kt has t dependence. So keep log h ket omega by kt as constant. Derivative of nkt you will get it as nk. That is the first term. There is a negative in the definition. And the second term is minus nkt into derivative of logarithm. It is 1 divided by h ket omega by kt into function of a function minus h ket omega by kt square. Because 1 by t derivative is minus 1 by t square. Okay, cancel the terms and you will get it as nk log. This minus sign again I absorbed into the logarithm and this becomes kt by h ket omega. So nk log kt by h ket omega plus 1. Equation number 7. This is the equation for entropy. Now you can calculate the internal energy U and it is given by A plus Ts. A plus Ts. We already have an equation for A and an equation for S. Substituting that you can find it as nkt. It is very simple. Multiply this s with the t, then you will get an nk into t, and the first term will cancel with this a. Okay, they are from the same sign, but in the logarithm they are opposite. H ket omega by kt is here, so here it is kt by h ket omega. So by taking a negative sign, you can write this as h ket omega by kt, and that term will cancel with the term in a. This is internal energy. By taking the partial derivative with respect to t, you will get CV, specific heat at a constant volume, and that will be Nk. Cp is the partial derivative of enthalpy with respect to temperature, but enthalpy H is equal to U plus PV. P is 0, that means enthalpy is same as internal energy, so Cp is same as Cv, and it is given by Nk. Now, we already mentioned about equipartition theorem in the last lecture. Equipartition theorem says that if there are f number of quadratic terms in Q or P, then the mean energy will be half FKT. Or each quadratic term in Q or P will contribute half KT towards internal energy. Here, our Hamiltonian is, for the first oscillator, it is half m omega square q1 square plus p1 square by 2m, plus for the second and plus for the third, and finally plus half m omega square qn square plus pn square by 2m. So, how many quadratic terms are there? 1 plus 1, 2. 2 for each oscillator. There are n oscillators, so there are total 2n quadratic terms. So replace this f with the 2n, then you will get again nkt. So this result is consistent with this. Okay, u is equal to nkt. This result we can also obtain from equipartition theorem. Okay. Now, we can find the density of states. Density of states from the partition function. We already done this for classical ideal gas in previous lectures. Using Bromwich integral, we can write an equation for density of states. G of E equal to 1 by 2 pi I integral beta prime minus I infinity to beta prime plus I infinity e raised to beta I qn of beta d beta with real part of that beta is greater than 0. Beta prime is the real part of beta. And here you substitute for q and beta as 1 by beta h cut omega raised to n, and in that 1 by h cut omega raised to n you can take it outside. The remaining is e raised to beta I divided by beta raised to n d beta. We can use contour integration to solve this, but we have to consider the cases for energy less than 0 and greater than 0 separately. So that we will discuss now. For energy less than 0, that is energy negative, our integration is from beta prime minus I infinity to beta prime plus I infinity. So you consider a straight line. From this real part is now this point is beta prime. So this point is beta prime minus Iy. This point is beta prime plus Iy. So this straight line is beta prime minus Iy to beta prime plus Iy. If you let y tends to infinity, this line becomes beta prime minus I infinity to beta prime plus I infinity. But in order to use the contour integration method, we have to close the contour. Now I can close this contour either on the right side or on the left side. Now I will close it on the right side, because when you take y tends to infinity, it will take the value, beta will take the value plus infinity. Okay, when y tends to infinity, this will cover the entire right side and beta will go to infinity, and is e raised to beta e. E raised to beta e. Since e is negative, beta tends to infinity means e raised to beta e becomes minus infinity. E raised to minus infinity, and that will converge. That will converge. But if you close it on the left side, as y tends to infinity, beta will tends to minus infinity. E is already negative, so this e raised to beta e will diverge. That is why we close the contour on the right side. Okay. Now, what are the singularities inside this contour? Our integrand is e raised to beta e divided by beta raised to n. Beta equal to 0 is a singularity. But beta equal to 0 is this point, and that singularity is outside the contour. So on and inside this contour, this integrand is analytic. Therefore, closed contour e raised to beta e divided by beta raised to n d beta is 0. But this is the answer for closed contour. This closed contour I can write the sum of this red straight line integral and this semicircle gamma. So I can write the closed integral as integral beta prime minus Iy to beta prime plus Iy plus the contribution from this semicircle gamma. But we will let this y tends to infinity, because we need the answer for integral beta prime minus I infinity to beta prime plus I infinity. When we let this y tends to infinity, the contribution from this semicircle will vanish. Okay, so I can say that this closed integral answer is exactly the same as integral beta prime minus I infinity to beta prime plus I infinity e raised to beta e by beta raised to n d beta, and that answer is 0. The closed contour integral answer is 0. Closed contour I can write it as the sum of two terms, but this term will vanish in the limit y tends to infinity. Okay, so for energy less than 0, density of states is 0. as we expected. Okay. Now, for E greater than 0, for energy greater than 0, we will close the contour on the left side. Why? Because there is an e raised to beta E. Now E is greater than 0. So in the limit y tends to infinity, this will go to minus infinity. Beta will go to minus infinity. E is positive. So this product will be minus infinity. So e raised to minus infinity will converge. If you close it on the right side, then beta will be positive, E is positive, so beta E will becomes plus infinity and E raised to plus infinity will diverge. That is why we close it on the left side. Now, we have Cauchy integral formula for derivatives. Cauchy integral formula for derivatives. 1 by 2 pi I closed integral f of z by z minus z naught raised to n plus 1 dz equal to f raised to n z naught divided by n factorial. In our case, instead of f of z, we have e raised to beta e. Instead of z naught, we have 0. Instead of z, we have beta. And instead of n plus 1, we have capital N. And our integral is this one. 1 by 2 pi I closed integral e raised to beta e divided by beta raised to n d beta. Substituting in the right hand side, you take n minus 1 derivatives. If you have here n plus 1, the derivative is nth derivative of f. Here you have capital N, so you have to take n minus 1 the derivative of this function. Here this function is e raised to beta I. And that has to be evaluated at z0. Here instead of z0 you have 0. Divided by n factorial becomes n minus 1 factorial. Taking the derivative of exponential, each time that will give you e. Each time that will give you an e. So n minus 1 derivatives means e raised to n minus 1. Finally, you will put beta equal to 0. So e raised to 0 becomes 1. So that will be e raised to n minus 1 by n minus 1 factorial. Again, in the limit y tends to infinity, the contribution from this semicircle will vanish, and this closed contour integral is same as integral beta prime minus I infinity to beta prime plus I infinity. So the density of states becomes g of e equal to 1 by h cut omega raised to n e raised to n minus 1 by n minus 1 factorial for e greater than 0 and 0 for e less than or equal to 0. We can find the value of density of states at e equal to 0 as 0 because we have for e less than 0 the density of states is 0 and for e greater than 0 this is the value, but if you put e equal to 0 in this you will get a value of 0. So it is a continuous curve up to e equal to 0, its value is 0, then it monotonically increases. This is the expression for density of states. It is equation number 10. Now, just for checking the validity of this equation, we will calculate entropy. Okay, we already calculated entropy, but we will calculate once again using this expression. Okay, this is density of states. In terms of density of states, entropy is k log g. Because we have entropy k log omega, where omega is the number of microstates. Here, g of e is the number of microstates corresponding to energy E. So substitute for this g, you will get it as k log 1 by h cut omega raised to n e raised to n minus 1 by n minus 1 factorial. If n is very large, you can neglect this 1. So e raised to n minus 1 becomes e raised to n, and the denominator n minus 1 factorial becomes n factorial. So this is nk log 1 by h cut omega plus n, this n will come to this side, nk log e minus, and this 1 by n factorial, log 1 by n factorial, you can apply Stirling's approximation and that will give you n log n minus n, n log n minus n. So solving this, nk log, here you have an e, here you have a 1 by h cut omega, so that becomes nk log e by h cut omega, e by h cut omega, and here there is an n, so that will come to the denominator. So So that is nk log E by n h cut omega plus nk. Nk can take outside. That will give you S is equal to nk log E by n, energy per oscillator. That is kt. So kt by h cut omega plus 1. Equation number 11. We can calculate temperature. Temperature T is dou S by dou E. If you take the derivative with respect to E for this expression, you will get it as E by Nk. That is very simple mathematics. You can calculate it as E by Nk. It is equation number 12. So this is all about the classical treatment. Here we calculated the partition function by integrating over the volume of phase space, Once we have the partition function, single oscillator partition function, we can calculate n oscillator partition function as single particle partition function raised to n, and here we considered the oscillators are distinguishable. Then we calculated various thermodynamic parameters like Helmholtz free energy A, chemical potential mu, pressure P, entropy S, internal energy U, specific heat capacities Cp, Cv, and then we verified the equipartition theorem. Then we find the calculated the density of states using Bromwich integral, and again using density of states we calculated entropy and verified the results are matching. Now we will move on to quantum mechanical treatment. Here we will consider the solution of Schrodinger equations as the microstates, and the possible energy values of a harmonic oscillator is given by En is equal to n plus half h cut omega. En is equal to n plus half h cut omega, where omega is the frequency of oscillator. N can take values 0, 1, 2, etc. And the partition function is defined as sum over all energy states e raised to minus beta En. Okay, n equal to 0 to infinity e raised to minus beta En. Substituting for this En, you will get this as like this. If you put n equal to 0, you will get it as e raised to minus beta half h cut omega. If you put n equal to 1, you will get it as e raised to minus beta 3 by 2 h cut omega, and so on. And this is the sum to infinity of a GP whose first term is e raised to minus beta half h cut omega, and the common ratio is e raised to minus beta h cut omega. We have the sum Sn equal to a divided by 1 minus r for r less than 1. Here e raised to minus beta h cut omega, this is less than 1 always. So you can write the partition function q1 beta as e raised to minus beta by 2 h cut omega by 1 minus e raised to minus beta h cut omega. Now this I can modify it like this. Take e raised to minus beta by 2 h cut omega from denominator. That will give you e raised to beta by 2 h cut omega minus e raised to minus beta by 2 h cut omega. This e raised to minus beta by 2 h cut omega will cancel from both numerator and denominator, and it can be written as 1 divided by, the denominator is nothing but 2 sin h beta by 2 h cut omega. 2 sin h beta by 2 h cut omega. This is single oscillator partition function. N oscillator partition function can be written as single oscillator partition function whole raised to n. Then this will give 2 sin h beta by 2 h cut omega whole raised to minus n. Okay, here it is in the denominator, so this becomes minus n. And you can also write from here, from this expression raised to n, that will give you e raised to minus n by 2 beta h cut omega into 1 minus e raised to minus beta h cut omega whole raised to minus n. Okay, so you can either use this expression for n particle or n oscillator partition function, or you can use this expression. Now, Helmholtz free energy. Again, we will calculate all the thermodynamic parameters. The only difference between classical treatment and quantum mechanical treatment is the way in which we obtain the partition function. Okay, so Helmholtz free energy is minus kT log Qn. Substitute for Qn. Then take a logarithm. This n will come to this side. So this is minus nkt log and exponential will cancel, minus beta by 2 h cut omega, and the next term is this minus will come here, this minus kt and minus n becomes plus nkt, log 1 minus e raised to minus beta h cut omega. So this becomes n, you can take it as common, this kt and beta will cancel because beta is 1 by kt, minus and minus becomes plus half h cut omega plus this ktn taken outside, then kt log 1 minus e raised to minus beta h cut omega. This is equation number 16. This is the equation for A. Chemical potential mu is the partial derivative of A with respect to n at a constant V and T. So there is the only term which contains n is this n. So when you take the derivative with respect to n, you will get the term inside this square bracket. So mu is simply a by n. It is half h cut omega plus kt log 1 minus e raised to minus beta h cut omega, and p is dou a by dou v at a constant n and t. There is no v dependence here, volume dependence. So pressure is 0. Now entropy is S is equal to minus dou A by dou T at a constant N and V. So when you take the derivative of this A with respect to temperature, here you have a temperature term, and in this term beta is 1 by kt. So here there is a temperature dependence. So you have to apply product rule. First you keep this logarithm term as constant and take derivative of t, that will give you 1. So first term is s is equal to, there is already a negative sign, minus nk log 1 minus e raised to minus h cut omega by kt, and the second term is keep this kt as constant, take the derivative of this logarithm, that will give you 1 divided by 1 minus e raised to minus h cut omega by kt, then function of a function, that will give you minus e raised to minus h cut omega by kt. You have to take again the derivative of this quantity, that will give you h cut omega by kt square. Okay, you cancel the terms and you will get it as minus nk log 1 minus e raised to minus h cut omega by kt plus this h cut omega by kt square, this t square 1 t will cancel here, and this remaining h cut omega by kt is here. Then this e raised to minus h cut omega by kt will go to the denominator, and this 1 by e raised to minus h cut omega by kt becomes e raised to plus h cut omega by kt, minus this will cancel with the denominator. So you will get it as minus 1. And this negative and this negative, that will become plus nk. So that is the second term. The entropy is nk into h cut omega by kt e raised to h cut omega by kt minus 1 minus logarithm of 1 minus e raised to minus h cut omega by kt. This is equation 19. Then internal energy U is A plus Ts. We already have an expression for A and S. Substitute, you will get as N into half h cut omega plus h cut omega divided by e raised to h cut omega by kt minus 1. It is a simple addition. You will get directly this relation. Then Cp, Cv both are the same because there is no pressure. So internal energy and enthalpy are the same. So specific heat at a constant volume is dou U by dou T. Specific heat at a constant pressure is dou H by dou T. But H and U are the same. So Cp and Cv are the same. You take the derivative of U with respect to T. Then you will get the second time nh cut omega, and 1 by e raised to h cut omega by kt minus 1. The derivative is minus 1 by e raised to h cut omega by kt minus 1 the whole square into e raised to h cut omega by kt into minus h cut omega by kt square. Okay, function of a function. That will give you nk into h cut omega by kt the whole square e raised to h cut omega by kt divided by e raised to h cut omega by kt minus 1 the whole square. Equation number 20. Now we will discuss the variation of energy per particle as a function of temperature. Here we are plotting energy per particle divided by h cut omega against kt by h cut omega because these are dimensionless quantities. Okay. So from this expression you can write energy per particle by h cut omega as half plus 1 divided by e raised to h cut omega by kt minus 1. If you plot this, you can see that when t is equal to 0, this becomes e raised to infinity. 1 by infinity is 0, so you will get half. So at this point you will get half. Then it monotonically increases as temperature increases. This is the graph of quantum mechanical oscillator, or we can call it as Schrodinger oscillator. Now we will consider the classical oscillator. Classical oscillator. For classical oscillator, the energy per particle or energy per oscillator is kT. So energy per oscillator by h cut omega is equal to kT by h cut omega. So if your y-axis is energy per particle by h cut omega, and on the x-axis kT by h cut omega, this is like y equal to x. So you will get a straight line. You will get a straight line passing through origin. As temperature increases, energy per oscillator will also increase linearly. Now we can consider a case which is known as Planck oscillator. Here we will not consider the 0 point energy. That is, at absolute zero, the energy of oscillator becomes 0. That is the case with the Planck oscillator. No 0 point energy. So the energy equation, there is no half h cut omega. So energy per oscillator is simply h cut omega divided by e raised to h cut omega by kt minus 1. So if you plot again energy per particle divided by h cut omega versus kt by h cut omega, that will be something like this. It will start from 0. At temperature 0, the energy is 0, then it monotonically increases. For a Schrodinger oscillator, at temperature t equal to 0, it is half, and then monotonically increases. Now I will plot all these three cases in a single graph. This green one is Schrodinger oscillator, red one is classical case, and this yellow one is Planck oscillator. As temperature increases, or at high temperatures, the Schrodinger oscillator becomes very close to the classical case. Okay, so at high temperature, we can say that the quantum mechanical behavior and classical behavior matches. But the Planck oscillator, the value is has a decrease or has a reduction by a factor of a half h cut omega. Okay, it is always reduced by an amount half h cut omega. The case of Planck oscillator. Okay, so as temperature increases, the classical treatment and the quantum mechanical treatment takes the same value, which is kT, which is kT. Okay. Now Cp and Cv given by the same expression. Cp and Cv is given by the same expression for both Planck oscillator and Schrodinger oscillator, because Cp and Cv is the derivative of u with respect to temperature, and this term is a constant. So irrespective of whether there is 0 point energy or not, the Cp and Cv values are same for Planck oscillator and Schrodinger oscillator, and this will limit to a value of Nk at a high temperature. Okay, it will tend to a value of Nk at high temperatures. Okay, you can see here the e raised to h cut omega by kt in the denominator becomes 1 plus h cut omega by kt. So that 1 will cancel, and h cut omega by kt whole square will cancel with this numerator. And in the numerator, this e raised to h cut omega by kt, you can approximate it as 1. So that will reduce to nk. So Cp and Cv will reduce to the classical value Nk at high temperatures. Also, for Kt very much greater than h cut omega, equation 14 to 21. Equation 14 to 21 means equation for single particle partition function or single oscillator partition function, then 15, and then Helmholtz free energy, and then chemical potential pressure. All these expressions up to 21 for the expression for Cp and Cv, they will reduce to their classical counterpart. What are their classical counterparts? Single particle partition function, that is equation 2, equation 2 to equation, I think it is equation 9. Cp and Cv, it is equation 9. Okay, so we can say that the quantum mechanical equations reduces to classical equations for very high temperatures. Now, as we did in the case of classical treatment, we will calculate density of states from partition function. There we used Bromwich integral, but here it is a little bit simpler. So the partition function Qn of beta is e raised to minus n by 2 beta h cut omega into 1 minus e raised to minus beta h cut omega raised to minus n. We have the identity binomial expansion 1 minus x raised to minus n is 1 plus nx plus n into n plus 1 by 2 factorial x square plus etc. And here the coefficients 1, n, n into n plus 1 by 2 etc. can be identified as sigma r equal to 0 to infinity n plus r minus 1 factorial divided by r factorial into n minus 1 factorial. So if you put r equal to 0, you will get 1. If you put r equal to 1, you will get n. If you put r equal to 2, you will get n into n plus 1 by 2 and so on. So this 1 minus x, the whole raised to minus n is equal to sigma r equal to 0 to infinity n plus r minus 1 factorial divided by r factorial into n minus 1 factorial x raised to r. If you put r equal to 0, you will get this first term 1. If you put r equal to 1, you will get the second term nx and so on. Now, this n plus r minus 1 factorial divided by r factorial into n minus 1 factorial can be represented in another way. This is an equivalent representation. N plus r minus 1 r, okay, in open brackets. So 1 minus x raised to minus n can be represented like sigma r equal to 0 to infinity n plus r minus 1 r x raised to r. Therefore, instead of x, here we have e raised to minus beta h cut omega. Therefore, that becomes sigma r equal to 0 to infinity n plus r minus 1 r e raised to minus beta r h cut omega. There is one more term e raised to minus n by 2 beta h cut omega. So, multiply with that. You will get sigma r equal to 0 to infinity n plus r minus 1 r e raised to minus beta n by 2 h cut omega plus r h cut omega. Okay, I think it is clear. Now, this is the partition function. This is the partition function. We have partition function equal to integral 0 to infinity density of states g of e into e raised to minus beta e dE. This is our definition of partition function once we have the equation for density of states. Also, from the definition of Dirac delta function, we have the familiar identity integral 0 to infinity f of x delta x minus x naught dx equal to f of x naught provided x naught lies between the limits. So here we can apply this identity in order to identify what is g of e. This is your Qn of beta. If your g of e is sigma r equal to 0 to infinity n plus r minus 1 r delta of e minus r plus n by 2 h cut omega, then if you substitute that here, this constant terms will come outside and this E will get replaced with R plus n by 2 h cut omega, and that is exactly here. E get replaced with R plus half n h cut omega. So using this identity of Dirac delta function, you can write an expression for g of e as sigma r equal to 0 to infinity and this thing. You can substitute back this and you can verify that you will get this Qn of beta. Okay, using this Dirac delta identity. Now, what is the meaning of equation 23? It says that if your energy is exactly R plus half n h cut omega, then you will have this many number of microstates. For any other values of energy, your number of microstates will be 0. Okay, what is the meaning of this equation? If your energy is exactly R plus half n into h cut omega, then you will have this many number of microstates. That is n plus r minus 1 factorial by r factorial into n minus 1 factorial microstates available to the system. I will explain that little more. Suppose your r is equal to 0. Suppose your r equal to 0. Then your energy will be half nh cut omega. R equal to 0, that means energy will be half nh cut omega. Each oscillator we can give an energy of half h cut omega, the 0 point energy. Then n oscillators you can give half h cut omega each. Then the total energy will be half nh cut omega. So we have only one possible microstate. There is only one possible way to distribute this much energy to n oscillators, because we have to give the 0 point energy to each oscillator. If you put r equal to 0 in this, if you put r equal to 0 in this becomes n minus 1 factorial by n minus 1 factorial, and that will be 1. Now suppose r is equal to 1. Suppose r equal to 1. Then you have 1 plus half n h cut omega energy. That is half n h cut omega plus h cut omega. In this half h cut omega each for n oscillators, that will give half n h cut omega. Then there is a remaining one packet of energy h cut omega. This you can give any one of the n oscillators. This remaining energy h cut omega you can give any one of the n oscillators. So you have n choices. You have n choices. So we can substitute here for r equal to 1. Then this becomes n factorial by n minus 1 factorial. That is exactly n. So in a similar manner you can proceed, and you can clearly say that when energy E equal to R plus half n h cut omega, there will be n plus R minus 1 factorial by R factorial into n minus 1 factorial number of microstates. For any other value of energy, the number of microstates will be 0. Here R can take values 0, 1, 2, 3, etc. Okay, so that's it. Now we will look into this problem in an alternate view. Let we have E energy to be distributed among n oscillators. Okay. Suppose we have an energy of E that have to be distributed among n oscillators. First we will give half h cut omega to each of the oscillator. Then it will be half n h cut omega. So the remaining energy is E minus half n h cut omega, and that should give us packets with energy h cut omega. Okay, the energy is discrete, quantized. Each packet has an energy of h cut omega. So we have to distribute this much energy, E minus half n h cut omega, as packets of energy, each having the energy of h cut omega. Then how many packets will be there? E minus half n h cut omega divided by h cut omega. This will be the number of packets. Let it be R. Let it be R. Then we can write E as R plus half n into h cut omega. E as R plus half n into h cut omega. Now the problem is distributing R packets to n oscillators. How many ways are there in order to distribute R packets to n oscillators? We have R packets. Suppose these blue spheres are packets of energy, and there are n oscillators. Suppose each of these boxes are oscillators. How many ways are there in order to distribute these packets in n oscillators? For that, first we will consider this simple mathematical problem. Suppose we have 3 squares and 2 circles. How many ways are there in order to arrange them? How many permutations are there in order to arrange these 3 squares and 2 circles? Answer is 3 plus 2 factorial divided by 3 factorial into 2 factorial. Total is 5, and there are 3 square and 2 circles. So the total number of ways is 3 plus 2 factorial divided by 3 factorial into 2 factorial. Answer is 10. What are the ways? These 10 possibilities I shown here. These are the different possibilities or different arrangements of 3 square and 2 circles. There are total 10 arrangements. But if we think in the same way, then for n oscillators and R packets, we may think that the number of arrangements is n plus r factorial by n factorial into r factorial. But that is wrong. Why? Because it is not possible to apply the same equation in our case. It is senseless that all packets are first and all oscillators are last, or vice versa. What is the meaning? In our case, they are not squares and circles, they are oscillators and packets of energy. All the oscillators first and all the packets of energy last. That doesn't make any sense because these packets should distribute over these oscillators. And all the packets of energy first and all the oscillators in the last. This also doesn't make any sense because these packets should be given to the oscillators. So it is senseless that all packets are first and all oscillators are last, or vice versa. So a way to avoid this is considering R packets and n minus 1 oscillators. Instead of n oscillators, you consider there are only n minus 1 oscillators. Then if there is an arrangement like all packets first or last, we can say that they will take by the remaining one oscillator because we are considered only n minus 1 oscillator. There is one more oscillator remaining. So if you consider this arrangement, all packets are the last, we can say that this packets will be taken by the last oscillator. That is the idea. So the number of arrangements, the correct equation is n minus 1 plus r factorial by n minus 1 factorial into r factorial. This is the same equation we obtained in this or in the earlier point of view. We obtained the number of microstates as n plus r minus 1 factorial by r factorial into n minus 1 factorial. So this is an alternate viewpoint, and again we obtained the same answer for number of arrangements or number of microstates. N minus 1 plus r factorial by n minus 1 factorial into r factorial. Using this value of microstates, number of microstates, we can calculate entropy is equal to k log omega. And when n is very much greater than 1, you can neglect this minus 1. So this becomes n plus r factorial. So logarithm of that quantity using Stirling's approximation, you will get it as n plus r log n plus r minus n plus r. And the denominator there is an n factorial, so minus log n factorial, again using Stirling's approximation, minus of n log n minus n, again minus log r factorial using Stirling's approximation, r log r minus r. So S is entropy is k into n plus r log n plus r minus n log n minus r log r. Equation number 26. Using this entropy, we can calculate the inverse of temperature. 1 by T is dou S by dou E, But here there is no E. But R is a measure of E. Okay. R number of packets, each having an energy h cut omega. So energy is R h cut omega. And there is of course the 0 point energy, but it is a constant. So you can write dou S by dou E as dou S by dou R into 1 by h cut omega. Okay, so this k divided by this 1 by h cut omega, k by h cut omega into derivative with respect to r, n plus r into log n plus r, derivative is 1 by n plus r, that term is here, plus log n plus r into derivative of n plus r is 1, that term, and the last term you will get minus log r. So the first term and last term combined together, you can write log r plus n by r. And then in this case, there is a second term r into 1 by r, and it is negative. So n plus r into 1 by n plus r, that will be 1, minus this also is 1, 1 minus 1 0. So you will get 1 by t as k by h cut omega log 1 plus n by r, 1 plus n by r. Okay, so you can substitute for R as E minus half n h cut omega divided by h cut omega. Rearranging this, you will get 1 by t is equal to k by h cut omega log. This h cut omega will go to numerator, and E minus half n h cut omega, you take it as the LCM. And finally solving, you will get E plus half n h cut omega divided by E minus half n h cut omega. Okay. This h cut omega and k will come to the left hand side, and taking exponential, e raised to h cut omega by kt is e plus half n h cut omega by e minus half n h cut omega. Cross multiply and group the terms, you will get it as e into e raised to h cut omega by kt minus 1 equal to half n h cut omega into 1 plus e raised to h cut omega by kt, or e by n is half h cut omega into 1 plus e raised to h cut omega by kt divided by e raised to h cut omega by kt minus 1. This is equation number 28, and this equation 28 is identical with equation 20. What is equation 20? We have u by n is equal to half h cut omega plus h cut omega divided by e raised to h cut omega by kt minus 1. So u by n is equal to, you take LCM and rearranging, you will get it as u by n is equal to half h cut omega into e raised to h cut omega by kt plus 1 divided by e raised to h cut omega by kt minus 1. This is exactly the same equation. So we again are consistent with our results. Now we can show that we will get the same expression for entropy as we obtained from equation 9. So you start with the equation for entropy. Here S is equal to K into n plus r log n plus r minus n log n minus r log r. Here we have to substitute this r in terms of t. For that we will use this expression 1 by t equal to k by h cut omega log 1 plus n by r. So how we will proceed, we will look into it. This is entropy S. This is k into r plus n log r plus n by r minus n log n by r. Here I added and subtracted one term. It is n log r. I added and it subtracted that same time, n log r. Then this minus r log r minus n log r combined, you can write it as minus of r plus n log r. And that term combined with the first term will give you r plus n log r plus n by r minus the last two terms, you will get, you can write it as minus n log n by r. Why? Because we have 1 by t as k by h cut omega log r plus n by r. Now you have log r plus n by r, so you can substitute it as h cut omega by kt. In terms of, in place of this logarithm, you can write h cut omega by kt. But what is r plus n? You have here, you can write h cut omega by kt as log r plus n by r, or r plus n by r is e raised to h cut omega by kt, or 1 plus n by r is e raised to h cut omega by kt, or n by r is e raised to h cut omega by kt minus 1. That will give me r is equal to n by e raised to h cut omega by kt minus 1. So substitute for this r, this value plus n log r plus n by r is h cut omega by kt minus n log n by r. N by r is here, so logarithm of that quantity. So s is equal to, this n you can take outside, nk into the first term you have h cut omega by kt divided by e raised to h cut omega by kt minus 1. N already taken outside, then h cut omega by kt minus this, you can write it as, take e raised to h cut omega by kt outside, then it is log e raised to h cut omega by kt. The first time you will have 1, the second time you will have an e raised to minus h cut omega by kt. Log a into b is log a plus log b, and log a, that is log into exponential, this will cancel and you will get minus h cut omega by kt, and that will cancel with this plus h cut omega by kt. The remaining is minus log 1 minus e raised to minus h cut omega by kt. This is exactly the same result we obtained from equation 19. Okay, so all the results are consistent. The results obtained by following the microcanonical approach and the canonical approach are asymptotically the same. Why we said that this is in the microcanonical approach? Because here we fixed an energy and distributed among n oscillators. So fixing an energy is the viewpoint of a microcanonical ensemble. So the approach using the microcanonical ensemble and the approach from canonical ensemble all will give you the identical results. So we again and again prove this same for different systems that the different approaches, the microcanonical approach or canonical approach, all will give you the identical results, identical thermodynamic results. Finally, we will consider the classical limit when E by N is very much greater than h cut omega. That is, energy per oscillator is very much greater than h cut omega. H cut omega is the packet of energy. So we can say that R, the number of packets R will be very much greater than number of oscillators. If you have 1000 packets and 10 oscillators, each oscillator will get around 100 packets. Okay, so E by N is very much greater than h cut omega, means that this R is very much greater than N. Then R plus N minus 1 factorial. It is R plus N minus 1 and R plus N minus 2 up to R up to 1. Divided by denominator, there is an R factorial into N minus 1 factorial. This R factorial will cancel the product of 1 up to R. Then the numerator you will have R plus 1 up to R plus N minus 1. Since R is very much greater than N, you can neglect this N minus 1, N minus 2 and up to 1. So there will be R into R into R into, there will be N minus 1 R's. So you can write it as R raised to N minus 1. R raised to N minus 1. Okay. Divided by N minus 1 factorial with R approximately equal to E by h cut omega. Because R actually it is E minus N by 2 h cut omega by h cut omega. But this N is very small compared to R. Therefore, you can neglect this energy, this 0 point energy you can neglect it because we are considering a very large amount of energy. So you can neglect this N by 2 h cut omega. Then R is approximately E by h cut omega. S is K log omega. This is the number of microstates. So K log R raised to N minus 1 by N minus 1 factorial. This N minus 1 will come to this side. Log A raised to B is B log A. N minus 1 K log R minus K into N minus 1 log N minus 1 minus N minus 1. This is Stirling's formula. But again, N is very much greater than 1. R is very much greater than N. But N is very much greater than 1. So you can neglect this once. So you can write it as Nk log R minus Nk log N plus Nk. So that is Nk into log R by N plus Nk. But R is nothing but E by h cut omega. So S is approximately Nk log E by N h cut omega plus 1. And 1 by temperature is dou S by dou E. And that will give you Nk into 1 by E by Nh cut omega into 1 by Nh cut omega. That is simply Nk by E. For this, I can write it as E by N is equal to Kt. So energy per oscillator is Kt. Energy per oscillator is Kt. So again, the identical results that we derived earlier. So in this lecture, what actually I explained is the treatment of N harmonic oscillators using classical approach as well as quantum mechanical approach. First, we calculated the partition function using phase space concept and we derived the entire thermodynamics. We derived the equation for different quantities. Then we treated the oscillators as quantum mechanically. We considered the Schrodinger equation, the possible energy values. Then using this expression, sigma n equal to 0 to infinity e raised to minus beta n, we calculated partition function. Using that partition function, we again calculated the different thermodynamic parameters. All are the same. Then we discussed the different cases, Schrodinger oscillator, classical oscillator and Planck oscillator. Then in the next session, we calculated the density of states. Density of states we calculated in the classical case using Bromwich integral. In the quantum mechanical case using binomial expansion, we can calculate the density of states. And in an alternate viewpoint, we again calculated the density of states, and in both cases we obtained the same expression. And using that expression, in the microcanonical approach, we calculated again entropy, energy per particle, etc. And all the results are consistent. Okay, all the results are consistent. So this is one of the most beautiful example for uh, the canonical ensemble system, and we can use the results from microcanonical ensemble also. Thank you.